Good evening, everyone. I am very pleased tonight to open up the series of lectures that are the beginning of the cluster of research on the theme of art, architecture, and energy. The title is Beyond Entropy, When Energy Becomes Form. And the aim of the collaboration between artists, scientists, and architects is to rethink the notion of energy beyond all the rhetoric of sustainability, all the rhetoric of ecology, and to really consider it in its value of a cultural force that is able to inform the way we relate to materiality, the way we manipulate reality, and the way through which we can really make sense of the space and the time where we are. And because of this ambition, it was really important to call artists, scientists, and architects who are really able to take a distance or to be not spoiled by all the rhetoric that we wrapped the notion of energy with. And that is why it's for me tonight such a great pleasure to introduce the very first two speakers of this series of lectures. Is Professor Roberto Trotta, who is an astrophysics from the Imperial College of London. Roberto has an impressive portfolio and an impressive career, and he managed to work in the CERN Institute in Geneva, and there are many incredible achievements and extraordinary research. And together with Roberto tonight, I have the pleasure to introduce Wilfredo Prieto, a Cuban artist who probably most of you know because he did an extraordinary performance a couple of years ago for Freezer Fair, and whose witty work relates definitely with the notion of energy, but in a very unexpected and poetic way. And I'm really looking forward for the presentation, and I hope that this lecture would be inspiring for you. And I really would like to question a very active response from your side with questions and with hopefully the beginning of a fruitful discussion. Thank you very much. And I let it to Roberto.
Thank you, Stefano. Good evening, everybody. It's a great pleasure and an honor to be here tonight and to inaugurate with Wilfredo this fantastic series. It's a great pleasure to be part of this exciting new adventure, which really, in my opinion, is exactly what we need. We need to transcend the boundaries between disciplines and between science and art, and this adventure with the Architectural Association is really well placed to do just that. I would like to thank Silvana and Stefano for getting me involved into this. I would like to apologize in advance to Wilfredo. I'm not going to be able to stay here for the whole evening. Unfortunately, I will have to leave shortly after 7. So, if I leave later on, it's not because I'm not enjoying the evening. I'm sorry, I have to leave. So I do apologize for that. Before I get started on some reflections from a cosmologist point of view about space and the shape of space, and this is the dark side of the universe, which is sort of the theme that I want to look at tonight, in particular the theme of dark matter and dark energy. I just want to, before I properly get into it, I'd like to start with plugging a little advertising here for the series of debates that we are holding at Imperial College London called The Big Questions. And we've had 3 debates so far, looking at the origin of the universe, the existence of dark energy, and the existence of the multiverse. But next week, Thursday next week, we are going to have a new debate about human spaceflight, science or spectacle. And Dr. Ian Crawford will debate the issue with Dr. David Clements. And you're all very kindly invited to come. If you can attend, we will be very, very pleased to see you there. Okay. So if we go back a few thousands of years, at the very beginning of our shared cosmology, we know that the cosmos was very different back then in the human mind. Our ancestors had a very different picture of cosmology, and a picture that was a geocentric picture where the Earth was at the center of a revolving universe with the different spheres, the sphere of the moon and the spheres of the planets, of the sun, and the sphere of the fixed stars revolving around us. Now, we now think that this cosmology is a very primitive cosmology, but actually, if you think back for a second, this is a very natural cosmology. If you look out and look at the sun rising and the stars going around in circles, it really looks like as if the Earth is at the center of a revolving universe. Sure, the motions of the planets are a bit different and need to introduce epicycles to account for them and so forth. But really, what we now think of as a very primitive cosmology was a very natural cosmology that held on for thousands and thousands of years. In fact, for several hundreds of years, several thousands of years, until essentially 400 years ago, this man revolutionized our view of the universe. Galileo did an extraordinary thing 400 years ago this year. As you know, this year is the International Year of Astronomy, which marks, in fact, the revolutionary observations of Galileo. What he did, he took a telescope that he himself had built and turned it to the sky. And by doing this, he was able to make a whole lot of discoveries which were impossible for the unaided eye. He discovered, for example, that the moon is not perfect, but has got craters and irregularities on the surface. He looked at Venus and discovered that Venus has got phases, just like the moon, which by itself was a proof that Venus cannot be rotating around the Earth. And he looked at Jupiter, and he discovered the 4 Galilean moons. Here you can see them, here, the 4 little dots, which still bear his name, which was the first discovery of objects in the universe which were not revolving around the Earth, but were revolving around a different celestial body. And so after Galileo and Copernicus and others, and Kepler and so forth, we moved on to a view of the universe where the Earth was no longer the center, but the Sun was at the center of the solar system, and the Earth is here, the 3rd planet of this system revolving around the Sun. And by now, we have explored the solar system by and large. We sent mechanized probes to all of the major bodies in the solar system. Here you see in this diagram, zooming out of our solar system, the Sun is here at the center, and you see here the outer planets. This diagram is too small to see the orbit of the Earth. You can see here the 2 Voyager probes, which were sent out at the end of the 70s. Those are now the probes, the most distant human artifacts in the universe, which are only now, about after 30 years of voyage, they are reaching the outer end of the solar system, and they're going to get lost in interstellar space. And so we'll take a closer look to all of the bodies of the solar system, the Sun, Mercury, and Venus, the inner planets, and the outer planets, Mars, Jupiter, Saturn, Uranus, and Neptune, all the way out to Pluto, which is, as you know, been demoted recently from being a planet to being something less, like a planetoid. And not only are we now capable of looking out in great detail to these wonderful bodies that make up the solar system, but we can look further out into the visible universe and map it out with great precision thanks to very advanced technology. You can see here the constellation like Orion, the familiar winter constellation, and the more we zoom in, the further out in distance we look, the more distant objects we observe, the further back in time we observe. The light from these distant objects has taken hundreds of millions, billions of years to get to us, and so the further out we look here with the Hubble Space Telescope, the further back in time we see. So cosmology is a time machine. And you can see that here we have left our galaxy altogether. Every one of these little dots in this picture is a galaxy. This is a galaxy, this is a galaxy, just like the Milky Way. Those galaxies, each one of them contains hundreds of billions of stars. And there are about 50 billion galaxies in the visible universe. And this image, it's an incredible zoom on a very little fraction of the sky. A fraction of the sky that is the same area of as the eye of a needle held up at about arm's length. And there are so many, about 3,000 galaxies are in such a tiny area of the sky. So if you imagine looking around yourself in all the sky, what a wonderful tapestry of cosmic structures is out there. Recently, the European Space Agency sent a spectacular mission, the Planck satellite, which was launched in May this year, whose mission is to map out the universe around us to even greater precision. And what the Planck satellite will do, it will look back in time through the galaxies, through the dark ages here at the very beginning, and we'll look back at the relic radiation, the cosmic microwave background, which is essentially the visible echo of the Big Bang. And what the Planck satellite will do, it will improve on current maps of the microwave background. This is a map of the universe as it was 380,000 years after the Big Bang. That's a real map, a real data coming from a satellite showing the distribution of temperature in the universe at this very early time. This is before galaxies were formed, before stars were formed. This is essentially before the onset of structure formation. And so this is literally, this map is the end of the visible universe. You cannot see past this point in time because the early universe was very hot, very dense, and therefore opaque. So we cannot look back further in time than this. That's really the edge of the universe. But as I'm going to tell you tonight, this is not the whole story. Even this big tapestry of beautiful objects which make up the visible universe is not all there is to the universe. Actually, it's only a minimal part of what is out there. And in fact, there is a dark side to the universe. In order to understand the dark side, to understand dark energy, we have to step back a second and go back to the location of a big intellectual fight about 100 years ago about two heavyweights of Western thinking, of science and physics in general. So, of course, those two were Albert and Sir Isaac. Sir Isaac, of course, Newton, the founder of gravity and the discoverer of the fundamental laws of gravity, and this vision of the universe as a clockwork universe, a universe made of rulers and clocks that all tick away at the same rate, and rulers that measure up distances all the same way. But Einstein came along in 1913 or so with this notion of general relativity, which completely revolutionized our conception of the universe and our very notion of space. And here come to a key concept for the following, and hopefully for our activities here as well, the notion of space in physics. Now, Einstein thought that space is not static and time is not static, but actually those two entities are dynamic and are linked together in one unique entity, which he called space-time, which is represented in this little diagram here by this sort of mesh. You can see that the Earth here, with its mass, determines the shape of space-time. In other words, space-time is a bending, dynamic entity that responds to the presence of mass by being shaped by mass. So the space-time continuum is not static, is not fixed and immutable, but it's actually dynamic. And the presence of mass bends space-time, creating curvature. And now if we look up at the moon, for example, we see the moon going around the Earth in a circle, and we think, well, the moon is going around in circles. But actually it's not. The moon is traveling on a straight line, but space-time is bent around the Earth because of the mass of the Earth. So if the Earth is here at the center, space-time is bent, and therefore a straight line in a bent space-time looks like a circle to us. So that's an extraordinary intuition, extraordinary geometric view of space, and one that had to be tested observationally, of course. When Einstein put out his theory of general relativity, this was just that, a beautiful geometrical theory for space and time that could be tested thanks to one of the most spectacular astronomical phenomena that you can ever witness, which is a solar eclipse. And so why was a solar eclipse needed to test Einstein's notion of space-time? Well, we can understand this by looking at the phenomenon called the deflection of light. So if we have a star here, which is hidden behind the rim of the sun, and starlight is coming in a straight line, as it passes past the sun, because of the bending of space-time I was talking about before, the light will be bent and deviated from its straight line trajectory, and it will come to us after the bend, like this. So if we now project back the apparent position of the star in a straight line, you will see that there is a discrepancy between the true position of the star and the apparent position of the star due to the deflection angle. And this deflection angle here can be predicted from Einstein's theory of general relativity, and it turns out to be exactly twice as big as the angle that Newton predicted under his theory of gravity. And so, of course, we cannot observe stars beyond the rim of the sun in daylight because it's day. And so we have to do this during a period of eclipse. Now, the 1916 solar eclipse expedition was scuppered by World War I, so people had more urgent business to attend to than going around chasing eclipses, unfortunately. But in 1919, 90 years ago, a suitable eclipse came along, and here you see the path of that eclipse going off. So that's the path of the totality. So along this line, you could see a total eclipse. And so the Royal Astronomical Society in Britain sent out not one, two expeditions to make sure, absolutely sure, that they caught the eclipse and they could verify or falsify Einstein's theory. So one of the two expeditions sailed to Belize, here off the northeast coast of Brazil, and they took beautiful pictures, splendid eclipse. Of course, at the time they didn't have CCD cameras, so when they came back, they developed the plates that they had brought with them. They found out that their plates were completely useless because there was a problem with the focus of the instrument, and so no measurements could be done. But fortunately, there was backup, and backup was in the form of the second expedition led by the famous astronomer Sir Arthur Eddington, who actually went out to the Isle of Principe in sub-Saharan Africa, and his expedition was plagued by all sorts of mishaps. He lost some of the equipment, then some of the stuff that he brought with him broke, then he was attacked by some tribal people, warriors, and so forth. And so finally, when he was all set up and ready to take the pictures of the eclipse, well, the weather was cloudy, so he sent back a cablegram saying, true cloud, hopeful. Turns out that, of course, you know the story, turns out that those pictures actually did confirm just about, that the quality was just about right to confirm Einstein's theory of gravity, and so overnight Einstein became that absolute superstar of science that we know him to be. And so his theory was confirmed by this experiment. Why is it important for us and for cosmology and for space? Because, in fact, this notion of space being bent by gravity and by the presence of mass is absolutely crucial to the fate of the universe. So imagine here, this is a picture of the universe starting here in the Big Bang, about 13.7 billion years ago, and then time flows in this direction. And so the universe expands in time, but if the amount of matter, of mass in the universe is sufficient to stop the expansion and bend it back on itself, we will get, at the end, a big crunch. So the universe will expand, stop expanding under the influence of gravity, turn around, and end in a reflection of what the Big Bang had been, like a big implosion. Or, if the mass in the universe is not quite sufficient to bend space back onto itself, the universe might continue expanding forever, but forever decelerating. So that's two possibilities. Distinguishing among the two, in other words, working out the fate of the universe, it critically depends on us being able to work out what does the universe contain, how much mass is there out there, will it be enough to bend the universe back on itself or not. But there is a third possibility, which is the one that our universe actually seems to be adhering to, which is the possibility of anti-gravity, or something that I'm going to call for now dark energy. And dark energy has got exactly the opposite effect. Instead of bending back the universe onto itself, it's making the universe accelerate its expansion. And so the universe will continue accelerating its expansion forever at an ever-increasing rate until everything will end in a big rip about 60 billion years in the future. So in order to distinguish between these three characteristics and sort of work out the global shape of the universe, if you want, what we need is a measurement of the mass in the universe, because it's the mass that is responsible for the bending. And so we've already seen that there is lots of visible mass in the universe if you go out and measure it. Here again, it's a beautiful picture by the Hubble Space Telescope. That's the deepest picture, the most distant picture we can take, given our current technology. And to be fair, you cannot take a picture which is much deeper than that, simply because if you go further out and in distance, you get to a point back in time where galaxies had not formed. So that's all there is. But actually, the most astonishing discovery of modern cosmology is that all that is visible in the universe makes up only about 5% of the cosmos. So this little 5% of the total is absolutely everything that we can see in the universe, and that's to say planets, for example, such as the Earth, or galaxies, such as, for example, the Sombrero Galaxy here, or alien life forms, for example, that might live somewhere in the universe. All of that makes up this 5%. 25% of the universe, 5 times as much, is dark matter, and the massive 70% is dark energy. And in the next 15 minutes or so, I'm going to try and give you a feeling for what we think those two mysterious dark components are, and in particular dark energy, and how we go about trying to discover more about them. So somebody saw it coming. There's no question there is an unseen world. The problem is, how far is it from Midtown, and how late is it open? And so we're going to try and figure out how late is the universe going to stay open for. So, but before I can tell you a little bit more about it, I'd like to convince you, first of all, that we have evidence that this dark stuff is out there. You might think, well, it's dark energy, dark matter. How do we know? If it's dark, we cannot see it. So how can we tell that it's out there? But, you know, you don't need to see stuff directly to be able to infer its presence. You can use slightly more elaborated ways of detecting something which is per se invisible. Here is how this goes. And this was pioneered by this funny character here, Fritz Zwicky, which was a Swiss American astronomer who in the 30s made the following discovery. He made this discovery looking at clusters of galaxies, but for our purposes, we can look at the galaxy, any galaxy will do. The Andromeda galaxy, for example, is our nearest neighbor galaxy. It's 2.2 million light years away. That's to say, the light from the Andromeda galaxy takes 2.2 million years to get to you. And it's quite beautiful to go out on a dark winter night, and if you can spot the Andromeda galaxy in the sky, if you know where it is, you're going to see it in the sky if it's a dark night. And it's not going to look like this to you, because that's taken through a powerful telescope. It's going to look like a little fluffy, unresolved object that you can just make out among the stars. And it's quite astonishing to think that the light from that object has left 2.2 million years ago, when the human race was not even fully developed yet. So anyhow, but that's how the dark matter puzzle came about. So what Zwicky said, he considered stars in this galaxy, and this is a beautiful spiral galaxy that rotates on its axis, it spins like this. If you consider a star out here, the star is held onto the galaxy by the force of gravity. But it's also being pushed out at the same time as it spins around, it's pushed out by the centrifugal force. And so the two have to be in equilibrium, otherwise the centrifugal force will win and the star will fly out of the galaxy as the galaxy spins around. And now the thing is, if the stars that are further out from the center should turn in a more slowly fashion, simply because gravity is weaker out there, and so if they go too fast, the centrifugal force will win and they will fly out of the galaxy. It's like when you go with your car, you take a turn, and you take the turn with too high a speed, you just go straight, simply because the friction that supplies the force that keeps you on the track is not sufficient to compensate for the centrifugal force. So you have to go more slowly if you don't want to fly out of the turn, and it's exactly the same here. So stars further out from the center of the galaxy, where most of the visible mass is concentrated, should turn more slowly. But actually, and that's this curve here, as a function of the distance, the velocity of the stars should go down if Newton's theory of gravity and Einstein's theory of gravity are right. But actually, Zwicky observed that the velocity of the stars keeps going on. It's constant with distance. It does not fall with distance. And this observation has been repeated over and over again in modern times, and we always find that all the stars rotate at roughly the same speed. They do not slow down with distance. And to this missing mass problem, there are only two possible solutions. Either our understanding of gravity is wrong, and Newton and Einstein were wrong, and gravity does not behave the way we think it does, but that's difficult. Or there is an extra component, an extra massive component to the galaxy that is invisible, that we cannot see, that is the source of the extra force of gravity that keeps the stars on the track. And that's a notion of dark matter. And this observation has been repeated over and over again, and so far, we still haven't found what the dark matter is made of. Now, there are other ways too to see dark objects. Here, for example, that's a picture I've taken out of my window down in South Kensington Imperial. And if a black hole were to fly out of my window, I would be able to see it here. Not because the black hole itself is visible, but because the black hole with its gravitational pull deflects and distorts the light rays coming to us from a distant object, and so inducing a characteristic pattern like this that sort of makes it visible to us. So again, distorting space. So you have this key notion of space being distorted by gravity. So if a black hole would fly over here, we would be able to see it because although the black hole itself is invisible, it deflects and changes the trajectory of distant light rays, like that. And now we can play exactly the same trick using not black holes, but distant galaxies. And we can play this trick using the best piece of machinery we have available, namely the Hubble Space Telescope, which is it has been really the workhorse of cosmology and astronomy for the past 15 years or 20 years or so. And it's a flying telescope, it's a space telescope. And of course, it's a very expensive piece of kit, but there's very good reason why astronomers pushed very hard to get an orbiting space telescope, because the Hubble Space Telescope is above the atmosphere, and that makes all the difference when you're trying to look for slight deviations in the shape of things induced, by, for example, by the presence of dark matter. Just to give you a feeling for how sophisticated this is, those are pictures of some galaxies taken with the best ground-based telescope. We have the Gemini North, an 8-meter telescope, which uses adaptive optics to try and compensate for the vibrations of the atmosphere. And those are the same galaxies now seen by Hubble above the atmosphere. And it's amazing. The change is amazing. And all the difference is the atmosphere. So now with this piece of kit, what we can do, we can map out the galaxies in great detail, and we can look for distortions in the shape of galaxies brought about by this phenomenon of the deflection of light that I discussed before. So if you have a distant galaxy and the light is traveling through the universe, very, very distant now, we're talking about billions of light years away from us, and there is a concentration of mass between us and the distant galaxy, the light will be bent in characteristic fashion and will give us a pattern like that, a bent shape of a pattern which is characteristic of the presence of intervening mass because of the bending of space-time. And this characteristic shape is called the Einstein ring. You can see it here. The blue ring here is one single distant galaxy which has been bent and shaped to the extent that it now looks like a ring. And it's called the Einstein ring. And that's a real observation made again by the Hubble Space Telescope, which shows that Einstein got it right, that Einstein gravity really works the way he predicted. That's another image where you can see this beautiful ring around the galaxy here. So the galaxy here at the center, like the galaxy here at the center, this is the galaxy that is doing the bending. It's the galaxy that is changing the shape of space-time, while the blue ring is the ring brought about by the distant galaxy. And that's another example here. And now I want to give you one final bit of evidence about dark matter, which is, I think, the closest you're ever going to get to see dark matter with your naked eyes. And because seeing is believing, here is my crown piece of evidence. That's a beautiful picture of the cluster Abell 2218, taken again by the Hubble Space Telescope. And you can see very well that there are arclets all over the place. There are bits and pieces of Einstein rings that are all over the place, this picture. And now, the interpretation of this is, for example, this red arc here is one arc that comes about because a distant red galaxy is being bent and shaped, the image is being bent and shaped by the gravity produced by the cluster, which sits here in the middle. Now, we can see the cluster, and we can work out how much visible mass there is. We can see the Einstein ring, and we can work out how much mass in total there is, because, as I told you before, it's mass that does the bending. It's mass that changes the shape of space-time. And we can compare the two, and the two are not the same. You need extra mass, invisible mass, to do the bending. The visible mass is not sufficient. And that's direct evidence for the existence of dark matter. Now, if dark matter exists, we don't know what it is. We are chasing it up very actively. We can simulate dark matter in a computer. That we can do. And we can do spectacular high-resolution cosmological simulations that take months of supercomputer time. Here is a picture that shows a chunk of the visible universe. This sort of chunk here is about 1/8 of the visible universe across. So on this sort of scale, the whole Milky Way would not even register. You know, we're looking so far away that this is every dot on this diagram contains many hundreds of times the mass of the Milky Way, and that's what we would see if we could see the dark matter in the universe. This sort of cosmic tapestry of dark matter distribution that's simulated 200 million years after the Big Bang, 1 billion years after the Big Bang. You can see that as gravity works its way through, filaments start growing and voids, which are the black spots, start becoming more prominent 5 billion years after the Big Bang and today. And so this is what the dark matter universe looks like according to our best theories. if we could see dark matter. We cannot see dark matter directly, but that's what we would see. So clumps of dark matter, which are the bright spots, are where the dark matter is clumped and where the dark matter accumulates, and that's where most of the bending of space-time takes place, and that's also where the galaxies grow, and that's where we find galaxies in the universe. And so you can see again a very beautiful filamentary structure that intersects, that has got multiple subclusters, which has got clusters of all sizes, like a big cluster here and a smaller cluster all around. And so this is a simulation of what the dark matter of the universe would be like. Now, this is, of course, a theoretical construction, but we are looking very actively, as I said, for the dark matter. If the dark matter is, according as some theories say, a new type of particle in the universe, then we should be able to reproduce it in the lab. And that's what CERN is going to try and do by smashing together high-energy particles, protons and antiprotons, which will go around at the speed of light in this underground tunnel, which is about the same size as the Circle Line in London, only engineered to a precision of a fraction of a thousandth of a millimeter, and which the Circle Line is not, unfortunately. So particles will be accelerated to almost the speed of light, and then they will be smashed together according to the old principle of smashing together high-energy particles and trying to look for something interesting in the debris. And because energy, according to Einstein, is equal mc squared, we hope that in the collision, new particles with large mass, like for example the dark matter particle, will be produced, and hopefully dark matter will be discovered like that. So really, before I devote the last 5 minutes of my time to dark energy, I would like to summarize the dark matter conundrum by this diagram, which is sometimes called the cosmic Ouroboros, meaning the snake that bites its own tail. It's an ancient Egyptian glyph that represents very beautifully this idea that as we go up from our sort of life scale of our ordinary life, go up in scale, look at planets, stars, solar systems, constellations, galaxies, and the whole universe, we go into the realm of cosmology, the macroscopic realm of the world. And as you go down this directional diagram, you go into the microscopic sub-millimeter scale, looking at atoms, nuclei, and eventually elementary particles, among them perhaps the dark matter particle. And it's interesting for me, and that's where the frontier of research and the frontier of my research lies, is up here, the point at which the two domains meet and probably merge, the moment at which the dark matter particle, which is a fundamental particle, subatomic particle, really becomes important and determines the evolution and the fate of the macroscopic universe, so the biggest case of cosmology. And that's what we're all after in the next few years at CERN and elsewhere. And so finally, we really have to address this elephant in the room. I told you about the dark matter, which is the 25% of the sort of the cosmic pie, but I haven't talked about the dark energy bit, which is the biggest chunk, and it's fair to say the most mysterious part. So here again is this cosmic pie. If you want visible matter, dark matter, and the big chunk, dark energy. So really the headline here is that 96% of the universe is missing, and we are looking for it. So dark energy has got a long and interesting story, which hopefully will be possible to explore further in other opportunities. We'll have more time to talk about it, but it goes back all the way to the great man himself again. Just to summarize it very briefly for you, in 1917, Einstein himself introduced a cosmological constant in his equations, which is, a cosmological constant is another word for dark energy. Because Einstein thought that the universe was static, you see. He didn't want to have an expanding universe, which his equations were telling him the universe was expanding. And so he introduced a cosmological constant, or anti-gravity, to balance out gravity perfectly, so that the universe was neither expanding nor contracting, a static, immutable, infinite, timeless universe. But in 1929, Hubble discovered that the universe is expanding after all, and Einstein realized that he had made a mistake. That had he not introduced the cosmological constant, had he not introduced the dark energy, he would have made the biggest prediction of all times, namely that the universe is expanding. But he missed out on that, because he introduced this dark energy term ad hoc to fix up his equations. So in 1934, he recanted and said that this dark energy thing, the cosmological constant, was his greatest blunder. But history comes back sometimes with a twist. And about 10 years ago, observations of stellar explosions called supernovae actually showed that Einstein perhaps was right all along, and the cosmological constant, that's to say dark energy, is actually out there. How do we know that dark energy is out there? Well, we look at stellar explosions called supernovas. So a supernova explosion is the spectacular end of the life of a particular type of star, a white dwarf here, that accretes material from a companion star, which is a red giant. And so the gas accretes on the white dwarf until the pressure of the gas is so high that the star cannot withstand this pressure anymore, and the runaway thermonuclear reaction is set off in the nucleus of the star that then explodes in a thermonuclear explosion, which is immense, which emits an incredible amount of energy and essentially transforms the star into a beacon that can be seen from very far away. Here is an example of supernova explosion. Down here, you can see that for a few days, supernova explosion can overshadow the combined luminosity of an entire galaxy, which is made of hundreds of billions of stars. So that's how much powerful this explosion is. That's a supernova explosion about 10, 15 years after it has gone off. You can see here the central remnant, here the core of the naked core of the star here in the center, and rings of plasma which are being expelled at about the speed of light into space. That's a supernova explosion about 1,000 years after it has taken place. And the reason we know that this particular supernova went off in 1054 is because it was so bright that it was visible in plain daylight. And so Chinese astronomers recorded it as a new transient star which was visible even during the day. And that's what remains of it now. And so here is how we hunt for supernovae. We look at galaxies and then we try and spot, like in these games where you spot the difference, try and spot a new star that wasn't there before. So I thought I'd just try with you, see whether you are keen observers. Can you spot the supernova in the right-hand side picture that isn't there in the left-hand side? Yeah? It's down here, right? So you can measure these supernovae, and by measuring them, you can measure distances in the universe. And the principle is very simple. The principle is the supernova are almost uniformly bright. So it's like having light bulbs in the universe, very powerful light bulbs. And so if I take a 60-watt light bulb from here and I place it 10 meters away, it will be dimmer. And if I place it 100 meters away, it will be 10,000 times dimmer and so forth. And so by measuring how dim it appears, if I know how dim it is, how bright it is, I can work out the distance. And that's exactly what we do in cosmology. And here is the astonishing discovery that as distance grows in the universe, the supernovae do appear to be fainter because they're further away. That's the usual thing you expect. But actually, turns out that the most distant supernovae are much fainter than you would expect. And therefore, the explanation is that dark energy, the tentative explanation at least, is that dark energy is stretching space, is changing again the shape of space between us and the distant supernovae, making them appear fainter than they actually are. And that's an almost direct piece of evidence of extra stretching, if you want, of space-time due to this mysterious component, which we call dark energy, for a lack of a better name. The thing is, we don't really know what dark energy is. The most plausible explanation is that dark energy is a property of space itself. And so here I go back to our theme of space and how we think about space in cosmology. And so empty space is not empty at all. Empty space is very alive with quantum mechanical processes, with particles that get created and destroyed all the time in a buzz of quantum mechanical activity that creates and destroys virtual particles all the time. And this quantum mechanical particle creation has got an energy associated with it, and therefore a mass associated with it. And the mass that you need, sort of the energy density or the mass density that you need associated with vacuum space, with empty space, to recreate the dark energy that could explain the supernova observations, is this quantity here, which is very, very small. It's 0.00030 gram, 64 gram per centimeter cube. So it's very, very small, but the universe is a big place, so there's lots of space out there. And now the point is that we do have theories of quantum mechanics, and you can go next door to your friends, the particle physicists, and ask them to predict this number based on the best quantum mechanical theories that we have, our best theories of physics. And they'll go away, they'll do a little calculation, and come back after a few days with a piece of paper. And on that piece of paper, they will have a number written on it. And that number, unfortunately, does not quite match the number that is observed in the universe. The difference is, frankly, embarrassing. The difference is this number here. it's really the most spectacularly wrong prediction in the history of science. So clearly there's something we don't understand here. And the key is that if you took away only 2 zeros of this immense number, chances are we would not be here to talk about it, because take away 2 zeros from this number and dark energy is too powerful. Dark energy would rip apart the universe by working as anti-gravity before galaxies have a chance to ever form. And so the question is, why are we here? Why is it that dark energy is just right for us and not too strong? Otherwise, we as human life forms, we would not be here to talk about it. No galaxies, no planets, no suns, no life forms, no humans. So that's the Goldilocks enigma, what Paul Davies in a book of this title calls the Goldilocks enigma. Why is the universe just right for life? And so you can basically take 2 different stances. You can take the stance that Richard Dawkins takes and say that the universe we observe has precisely the properties we should expect if there is at bottom no design, no purpose, no evil, no good, nothing but pointless indifference. Or, if you side with Fred Hoyle, the famous astronomer, the universe is a put-up job. So we don't have an answer to this question right now, but I just want to finish by giving you a tantalizing hint of an answer or a path for further reflection, perhaps. And the notion is the notion of the multiverse. And the multiverse is the notion that the universe, as vast as it is, it's not all there is to the universe. Actually, the universe is a collection of universes which are represented in this symbolic diagram by different spheres, and each one of those pocket universes, if you like, has got its own laws of physics, it's got its own constants of nature, in particular it's got its own dark energy properties, and so most of these universes will be so weird and so unhospitable to complexity and to biological systems that nobody will be there, but some of those universes will be just right, just out of chance, purely because of probability theory. Some of those universes will be just right, and we are bound to be found in a universe that is just right for us. And now, there is even some theory which is called like string theory that appears to predict the existence of such a multiverse, a collection of 10 to the 500 parallel universes. Now, if you try to imagine what 10 to the 500 means, it's this number here. So, among all of these universes, the theory is there will be one or a few that are just right for life without having to invoke a divine principle, just purely because of chance. So, here is the picture that we are left with to conclude. A universe that is a multiverse that is perhaps a collection of universes, each one with their own laws of physics, and each one possibly infinite in extent, out of which we can only see a little tiny patch, which is bounded by the time that light has got to travel from distant reaches of the universe to us. And so really we have made big progress in a way, in a sense, starting from the ancient cosmologies to the heliocentric view of the solar system, to understanding that we live in a galaxy, the Milky Way, that is but one among many other galaxies in the universe, which itself perhaps is only a little part of reality. So in a way, cosmology is marching on, and the questions that people asked so many years ago are still there with us in a sense, so there's still work to be done, and it's exciting to do this work, but also to reflect about this from a different perspective, which is what I hope we will achieve in this fruitful collaboration. And it's very exciting for me to be part of this because it allows us, the scientists, to see our own work with fresh eyes and try to interpret our own works with fresh eyes. And I'm very much looking forward to the discussions with the fellow researchers in the cluster. So to conclude, we could perhaps conclude with Einstein's question, or with Einstein's outlook on this. What I'm interested in understanding is whether God did have a choice in creating the universe. That's a very deep question. If only God would give me some clear sign, like making a large deposit in my name in the Swiss bank, things would be a lot easier. Thank you very much.
I think that what is really traumatic for humans in general is to understand the complex and the counterintuitive nature of reality. And this is obviously a challenge for all human beings. And on the other is really shocking to realize how poor and how banal is our conception of space. Above all, I mean, for architects, it's really depressing to imagine that all this richness is always like denied, forgotten, and totally blended into this like a notion of space as a set of measurable entities. And I think that the best way to really introduce the second speaker tonight, Wilfredo Prieto, is really to see how real artists with like an unspoiled view over things can really show how problematic can be our perception and our understanding of space and time. So I'm very pleased to like find like a natural continuation of the questions posed by Roberto with the presentation of Wilfredo Prieto. Thanks.
First of all, thanking Stefano for the invitation, and thanks to me for the translation. He apologized himself for not speaking in English, and he thinks that speaking Spanish is much more direct, and he thinks that he's going to compensate this lack of direct communication in English. When Stefano first commented me to come here to speak about my work, I was a little bit scared because, in a way, when you are talking about something as trendy as energy and so on, you are always having the risk of remaining superficial.
Y sin embargo, siempre he pensado que el arte, como trabaja con la experiencia, como mismo puede trabajar la arquitectura, la ciencia, cuando se trabaja en grupo todo cambia, ¿no? Hay otra visión mucho más profunda del asunto, ¿no?
But I thought that when we are talking about art, as long as it's concerning experience, in the same way that is science and architecture also concerning experience, the working as a group is going to be very helpful.
Por lo tanto, esta especie de comunidad que se pretende establecer en este experimento, creo que forma parte del camino que yo puedo traer en mis experimentos, o que pueden traer los arquitectos, los ingenieros, o todo ese conjunto, ¿no? Se puede complementar.
I think that this working in groups is going to be really important for me in the development of my art, and I think that it's going to be a really good experience to put together my work with the work of another colleagues coming from architectural sciences.
Lo más didáctico que podría intentar entrar en esto, y así de una manera me lo explico yo mismo, es que en el arte siempre hay dos cuestiones fundamentales. Uno, el qué decir, y otro, cómo decir.
The most didactic way to introduce my work would be questioning myself two very relevant questions in art. One is what to say, and the second one is how to say it.
Y en el sentido de qué decir, me preocupa más la idea de, o sea, en general mi trabajo siempre intenta indagar sobre diferentes niveles de interpretación en el arte, diferentes caminos de leer arte.
In this sense, my work is always instigating different ways of understanding art.
Por lo tanto, me interesa mucho ese grado superficial, esa idea de moda de, por ejemplo, esto mismo, la energía, ¿no? Y a la vez la idea más profunda del fenómeno en general.
So in this sense, I'm very much interested in this idea of energy as a trend, as something superficial, but at the same way I'm also interested in energy as something transcendental and deep.
Y en el sentido de cómo decir las cosas, pienso mucho en cómo necesita recibir el arte nuestra generación, ¿no? Nosotros, nuestra época.
And also very interested in how art has to be receptioned by our generation, how it's going to be communicated to our generation.
Y en ese sentido tenemos nosotros como una chispa de leer las cosas mucho más rápido, en un segundo, ¿no? Como tener una información, captarla en un segundo, compactada, llevarla a casa y luego digerirla, pensarla sobre ella, ¿no?
So in this sense, we are able to receive information in a much quicker way. We are able to receive much more information. We are able to receive a large amount of information that later we are going to reflect on it in home.
Creo que es una manera que hemos aprendido de la información, ¿no? Y en ese sentido el arte toma de la propia realidad complemento, ¿no? Como complemento.
So it's something that we understood about information, and art is part of this world in which we are living today.
Este primer trabajo que les muestro es del 99, o sea, hace 10 años. Les voy a mostrar como una visión muy general, muy pequeña sobre todo lo que he estado indagando.
This is first work that I did in 1999. I'm going to show you a very broad idea of the work I'm developing now.
Esta pieza se llama Arte Óptico. La hice en el contexto donde Cuba vivía una situación económica compleja. Se caía el campo socialista y entraba en un bloque económico con Estados Unidos, ¿no?
This piece is called Optical Art and is reflecting on a very particular economical condition in Cuba. There was the failure of the relationship with the social states and a new kind of dealing with the United States.
Lo que hice fue pintar en un campo gigante de árboles de mango, cuando estaban todos verdes, pintarlo de rojo en la realidad.
So what I did is to paint a forest of mango trees on red, but I was actually painting the real mango trees.
Y entonces jugaba con la ilusión de la gente, o sea, la gente tenía esa idea de la ilusión, el deseo, ¿no? Iba a tomar los mangos, ¿no?
So people had this illusion that the mangoes were already existing as red, and they went there to eat them.
Avalancha es una pieza que consiste en una serie de objetos esféricos organizados de menor a mayor.
So avalanche is another piece where a collection of objects are arranged according to a scale from the smaller to the bigger one.
Lo importante era como crear una forma muy material y a la vez contraponerla con una sensación muy imperceptible, ¿no? La idea del coleccionar, del organizar poéticamente un objeto, ¿no?
So it was a relationship between very condensed matter with a very visual experience. So it was a kind of artistic, poetical organization of matter.
La pieza era como muy kitsch, iban objetos esféricos desde cualquier tamaño, desde todo funcionando, ¿no?
I was putting together very different spherical objects, and many of them were very kitsch.
Eran 50 metros de largo con objetos de todo tipo, ¿no?
So 50 meters long, with all kind of different objects.
Al final había como una persona dentro de un bar esférico repartiendo vodka con naranja, ¿no?
The last one was a spherical bar with a bartender serving vodka with orange.
Escala de valor es una pieza que estaba puesta en una esquina del espacio de la galería, muy en el piso, ¿no?
Scale values is a small piece situated in a corner of the gallery on the floor.
Era simplemente 5 vasos plásticos como este.
It was only 5 plastic glasses like
El
this one.
primero con ron, el segundo vino, cerveza, refresco y agua.
First one was rum, the second one wine, the third beer, the fourth
Soft drink and water.
soft drink and water.
Grasa, jabón y plátano.
Green,
Es una pieza que juega con una tensión en el espacio, ¿no? En la arquitectura.
so grease, soap, and sorry,
Grasa, jabón y plátano.
and banana. I was playing with the sensation in the space.
Es la idea de cuando entras en un espacio tienes todo un placer, ¿no? Tienes un control sobre el espacio, pero sin embargo sientes que hay un punto que crea una tensión entre el espectador y la obra, ¿no?
It's this idea that when you enter into a space, you are enjoying a lot this space, but there is always a point of tension, a tension between the space and the person who is inhabiting it.
Y era como crear una imagen muy directa, muy literal, pero que a la vez hablara del cambio, ¿no? De un cambio de estado, ¿no?
So it's talking about a very literal a change in the mood of the person who is inhabiting this space and is represented with this banana.
Estaba en un espacio de 60 metros de largo por 10 de ancho.
The space is quite big, it's 60 meters long by 10 meters wide.
Esta obra es simplemente una grúa que intenta levantarse a sí misma.
This work is only a crane that is trying to unlift itself.
Y es una obra que habla sobre el poder, ¿no? Sobre la misma idea de la serpiente que se muerde la cola, ¿no? Que estaba hablando en el...
It's talking about power, it's talking about this idea of the serpent that is beating his own tail.
Y en eso, o sea, los motores de la grúa estaban completamente tensos, ¿no? Y funcionando todo el tiempo, pero con una tensión completa.
The engines of the car were really trying to pull up all the elements.
Y daba una sensación de levitación, como se sostiene en las puntas, ¿no?
So there was a kind of strong sensation of levitation in the air.
Esto es un performance que es completamente invisible. Lo que hice fue virar solamente las huellas del zapato al revés.
This is an invisible performance. The only thing I did is change the... What did you change?
Virar las suelas del zapato al revés. La base.
The base of the shoes were swapped around.
Y son simplemente caminos y recorridos que hago, pero prácticamente la gente no lo sabe, ¿no? Y estoy como creando un trayecto inverso, ¿no?
So it's creating a kind of reverse trajectory of the person who is walking.
Juego con la idea de cuidar la espalda, ¿no?
So it's playing with the idea of minding your back.
Esto es una pieza que hice en La Habana. Es una pieza que habla sobre la utopía.
This is a piece that I worked out in Havana and it's talking about utopia.
Es una pieza que tuve durante un mes en una galería.
It's a piece that was in a gallery for 1 month.
Lo que aparece a la derecha o a la izquierda, no sé. La máquina de allá.
The machine over there on the right.
Es un generador eléctrico que gasta 250 litros de petróleo por hora.
It's an electrical generator that is wasting a lot of gas.
Y una máquina, un camión de agua.
And the other one is a truck with water.
Y estaban haciendo mucho ruido fuera del espacio.
Making a lot of noise outside the gallery.
Y cuando entrabas dentro de la galería,
when you get into the gallery,
seguías los cables de electricidad y la manguera del agua, ¿no?
you were following the electrical wires and the water pipe.
Y contrastaba con el silencio absoluto del espacio de la galería.
And was in high contrast with the silence in the gallery.
Y entonces la electricidad daba un pequeño bombillo, un pequeño foco de luz.
So the electricity became shiny at a certain point.
Y la manguera de agua goteaba de 3 a 4 gotas diarias a una planta.
And the pipe was dripping like 3 or 4 drops of water every day.
También era como una obra
to a plant.
Era como una obra muy invisible, ¿no? Como entrar como una especie de construcción y formar parte, o sea, que la realidad formara parte de la obra, ¿no? Cortar esos límites entre el espacio de galería y la realidad, ¿no?
So it was again a very invisible work of art, and it was this notion of making everyday life part of art.
Y a la vez como hacer algo muy cursi, ¿no? Muy kitsch.
And again, making something really cheesy and really kitsch.
Esto es una pieza que el título es obligatoriamente al inglés, no se puede traducir en otro idioma.
This is a piece
$1 million.
whose title cannot be translated into Spanish, and is $1 million.
Y es simplemente $1 con 2 espejos.
It's only $1 with 2 mirrors,
Que se proyecta infinitamente.
infinitively projected.
Y la idea con esta pieza es realmente cuando lo exhibo en museos, en galerías, el espacio lo asegura realmente por $1 million.
And what I'm always getting when I exhibit in this work is that the gallery is able to give the assurance value of this work for $1 million.
Y también es la idea de crear una ilusión, crear un mito real
So
desde
it's,
la ficción.
so it's again this idea of creating a myth, of creating an illusion from the actual reality.
Esto es una pieza que son todas las banderas del mundo hechas sin los colores, ¿no?
This is a piece that is all the flags in the world, but without the colors.
Y respetando, o sea, teniendo el diseño original, la tela original, el material original.
It's having the original fabric, the original material, the original design.
Y es una pieza que generalmente cuando participa en un espacio cambia la significación del espacio y no el espacio cambia la significación de la pieza.
It's normally the piece who is changing the meaning of the space, and not the space who is changing the meaning of the piece.
Esto es en el Louvre en París.
This is in the Louvre in Paris.
Y es una, siempre la pieza como trata de hacer como una cofradía de adversarios, ¿no? O sea, hace una identificación desde puntos diferentes de entender la realidad, la política, ¿no?
So he's always trying to make a statement about different views of seeing the politics.
Esta es una vista en la Bienal de La Habana.
This is in la Bienal, in the Bienal in Havana.
Mudo es una pieza que lo que hice fue como cambiar el crear una discoteca en un museo, pero quitar absolutamente todo el sonido, ¿no?
Mute was about creating a disco club inside a gallery, but without the sound.
Y entonces era como crear una atmósfera en lo banal y en lo precioso, ¿no? Como ir un poco a lo estético puramente, ¿no?
It's about creating a very superficial and banal representation of the disco, and always relying only in this preciosism of the beautifulness of the lights and the colors.
Y era un poco como crear una pintura tridimensional en movimiento, ¿no?
It's about creating a three-dimensional painting and in movement.
Esto es un pequeño garbanzo
This is a little pea.
que tiene 5 milímetros de diámetro
It's 5 millimeters of diameter,
y era simplemente el dibujo del globo, ¿no?
and it's only
Perdido así en el espacio, ¿no?
the drawing of the globe lost in the space.
Esto es una pieza que creé con 6.000 libros en blanco.
It's a work that I created with 6,000 books, but with with nothing written.
O sea, era completamente anular la imagen, el texto, la información.
It was about avoiding the text, the image, the information.
Y era una forma de crear una nueva imagen a partir del vacío.
It was a way of creating a new kind of image from the void.
Y era algo que la gente podía participar, ¿no? O sea, normalmente el público cuando iba movía mecánicamente el libro como si estuviera leyendo algo, ¿no?
Normally people were participating on this, and they were performing and mechanically opening the books as if they were full of information.
Y normalmente cambiaba el tipo del papel, la textura del material, las dimensiones.
The materials and the dimensions and everything were changing.
Esta es una versión en la Bienal de Venecia.
This is another version in the Venice Biennale.
Esta pieza, Paseo, es un recorrido que hice con una planta ornamental durante 5 kilómetros.
This walk is a promenade that I did with an interior ornamental plant.
Y era simplemente eso, ¿no? Como movilizar un estado de quietud
It was about that, about mobilizing something that normally would be static inside a house.
Esta pieza que es vaso medio lleno,
This work is glass half full.
era simplemente un vaso lleno exactamente hasta la mitad de agua.
Is a glass exactly half full
Y
with water.
era simplemente una contradicción del título, o sea, y la forma, ¿no? Contenido.
It's a contradiction of the title and the final shape of the work.
El tiempo es oro es una pieza también muy limpia, ¿no? Solamente la imagen es totalmente literal.
The time is gold is also a very neat work and it's totally literal. The image is literal.
Es un reloj de oro funcionando con el tiempo exacto.
It's a watch made of gold and working with the exact time.
Y esto ya pertenece al último trabajo que estoy haciendo, que es un trabajo que intenta como crear obras prácticamente dentro de la realidad, completamente invisible.
This is part of the last things I'm working now and is trying to introduce art into the reality, into everyday life.
Y es una piedra, mierda humana y agua.
Is a stone, a piece of human shit and water.
Y son obras que se van relacionando con el espacio, ¿no? Casi es como hacer más un trabajo de arqueólogo, que el contenido está ya en la propia realidad más que una transformación que tú haces desde el punto de vista artístico.
This is more like the work of an archaeologist. The reality is already there, and the artist, the only thing has to do is to unveil this reality.
Y entonces simplemente como crear composiciones que puedes encontrarte, ¿no?
So it's creating compositions that could be already there.
Café con leche.
Coffee and milk.
Esta es una pieza que también realicé en Japón, que era la idea de hacer una variación de un objeto natural, pero dando un corte artificial, ¿no?
This is a piece that I realized in Japan, and it's about creating something that is real, but from a kind of totally artificial perspective.
Que también hablaba un poco de la idea de como el jardín japonés, ¿no? Que cuando das un corte a una planta estás haciendo una transformación artificial, pero que realmente lo que hace es ayudar a que esa planta crezca mejor, ¿no? Es como un movimiento artificial, pero que ayuda al desarrollo de ese natural, ¿no?
It's like in the Japanese garden when you are cutting the plants in a very artificial way, you are helping them to grow in a natural way.
Estas son otras intervenciones así completamente invisibles en la ciudad, una serie de charcos.
These are all the very invisible interventions in the city,
Pero es agua bendita por un cura de una iglesia.
but it is Christianized water by a priest in the church.
Y siempre estaban como en zonas que casi no puedes ni descubrir, ¿no? En la ciudad.
It's always in places in the city that is very difficult to discover.
Esta pieza es cambiar el sistema de un ventilador. O sea, un ventilador que normalmente dice no, y el otro cambiar el sistema para que dijera sí constantemente, ¿no?
So there's a couple of fans. One, they change the way in which they work. One is always saying yes, and the other one is always saying no.
Y entonces hacías como una especie de participación dentro de cuestiones así radicales, simples, ¿no?
So you were making a participation in very simple questions.
Esto pertenece a la misma serie del trabajo con la grúa, ¿no?
This is part of the work, the same work series.
Y es simplemente un cable de electricidad se vuelve a conectar a sí mismo.
It's electrical wire that is connected and is a closed circuit.
Aquí, aunque parezca que no hay nada, lo importante es el punto, ¿no? Que
Although it seems there is nothing there, there is a small dot, which is important.
y es una intervención que realicé en La Habana, que lo que hice fue poner una estrella artificial en el cielo, ¿no?
This is an intervention that I did in Havana, and what I did is to put a fake star in the sky.
Y era simplemente que tuvieras o sea, el paisaje, pero sin embargo vieras un punto nuevo, una estrella nueva y totalmente camuflajeada, ¿no?
So it's like seeing a natural landscape, but you have a new star, a star that is fake, but is totally hidden into reality.
Esto, como es muy difícil de fotografiar para que se vea cómo funcionó, era un globo aerostático transparente que no se veía, y ese globo a 300 metros de altura tenía un foco de luz LED que se iluminaba exactamente igual que una estrella, ¿no?
So this was because it's very difficult to see in this video. It was an aerostatic globe that has a light, and it was 3,000 meters from the Earth.
Y la luz tenía la misma intensidad de una estrella, ¿no? Podías camuflajearse perfectamente con el espacio.
The intensity of this light was apparently the same intensity of a normal star, so it was very easy to confuse this fake star with a normal star.
Término medio es una pieza que simplemente era con las sensaciones de creando espacios calientes, fríos, que tú podías transitar.
Middle term is just playing with different sensations of having hot or cold environments.
Y tú ibas transitando y cambiabas radicalmente la temperatura, ¿no?
You were going along this space and the temperature was changing very drastically.
Y entonces, vaya, en esa invisibilidad lo único que veía eran las cuestiones técnicas, ¿no? O sea, por dónde salía el frío y el calor, pero si no era completamente el espacio vacío, ¿no?
In this invisibility, you were only able to see the technicalities that produce this effect of being warm or cold, and besides this, the space was totally void.
El Smart es simplemente el gesto de organizar pegar chicles en el suelo, pero organizado, ¿no?
Smart gum is just sticking to the floor, chewing gums, but in a very organized and structural way.
Además que es una pieza que hice con chicles que la marca se llamaba así también, Smart Gum.
So the brand of these chewing gums is Smart Gum as well. It's very literal.
Y para terminar le voy a presentar dos proyectos en los que estoy trabajando ahora.
So to just do the map, I'm going to show you two projects I'm working now on them.
Este es un proyecto que voy a hacer en el 2011.
This is a project that I'm going to do in 2011.
En un campo de fútbol en Madrid. No es este es solo un ejemplo.
In a football ring in Madrid, stadium, Madrid.
This is an example.
This is not the actual stadium in Madrid, this is only an example.
Y la idea es convertir en el terreno en un lago, que dé una sensación muy oriental, ¿no? Como muy del placer visual simplemente, ¿no?
So my idea is to transform the central area of the stadium into a lake. So there is a kind of oriental taste for just enjoying your view with these reflections and lights in the water.
Crear un ambiente con 300 o 400 patos, con flor de loto, bambú.
So I want to bring in 300 ducks, bamboo, lotus flower, and so on, very oriental.
Y simplemente es eso, de dar un punto de vista del placer, pero totalmente artificial, ¿no?
So he's making a point about pleasure, visual pleasure, in a very, very artificial way.
Y este es el otro proyecto en que estoy trabajando ahora mismo con un grupo de físicos.
This is another project I'm working on now with a group of physicists.
Y la idea es hacer flotar una papa caliente en el centro del espacio, ¿no?
The idea is to make a hot potato be floating in the space.
Y la solución práctica ahora es mediante aire a presión.
Practical solution now is with compressed air.
Pero el problema es que tendría un hoyo en el centro del espacio, ¿no?
The problem is that you will have a hole in the middle of the space.
Y es solamente un problema estético, ¿no? Que estoy tratando de solucionar completamente y lo estoy investigando a ver si se puede resolver mediante imanes.
So it's a statistical problem, and I'm trying to solve this and trying to make an alternative solution with doesn't require the hole.
Y esto es todo, ¿no? Por el momento.
And that's everything. Thank you.